This episode is about cryptography and prime numbers. Say you want to send a company your credit card information. You want to be sure that nobody can see that information except you and the company you're sending it to. Cryptography is essentially the study of coding and sending secret messages. One of our most widely used cryptographic systems is something called Rsa Cryptography. The whole thing rests on a fundamental, easy to understand property of whole numbers. Whole numbers are the numbers we're most familiar with. 5, 8, 72, no decimals, no fractions, no ugly stuff. Take a whole number like 6. You can see that 6 is made of groups of smaller numbers. 3 groups of 2 or 2 groups of 3. It can be divided by 3 or by 2. If I try to divide it by 4, I get 1.5, and that's not what we're looking for. Most whole numbers can be divided evenly by other whole numbers. 10 can be divided by 5 and by 2. But 5 doesn't work like this. Neither does 2. Nothing divides these numbers except themselves and 1. Same with 3, 7, 11.
Those are primes. 2, 3, 5, 7. Those are all prime numbers.
These numbers are called prime numbers. They can't be nicely divided by any other whole numbers. Numbers that aren't prime are defined by which primes divide them and how many times those primes divide them. Only 6 can be divided by 3 once and 2 once, and only 10 can be divided by 2 once and 5 once. When you have humongous numbers, numbers that are hundreds and hundreds of digits long, it's really hard to figure out which prime numbers divide them. It's even super hard for computers to do it. It can take decades for a computer to figure it out. This is the basis of Rsa cryptography.
Hi, I'm Alan O'Day. I'm a security architect at Verifin. Verifin is a system designed to detect money laundering and fraud and help banks comply with banking regulations. So we use cryptography to protect the data that goes through those systems. It's very sensitive data, and we use it also to make sure that only the appropriate people can see it.
And how big are the numbers that you guys use in actual cryptographic systems?
We use numbers between 3 and 600 digits long. Big, giant numbers.
All right, so we're going to demonstrate a very, very rudimentary approximation of an RSA cryptographic system. You ready for this?
Yes, I am.
Okay, so first, if we have a message that's written in English and we want to somehow encode it using a number, how do we do that?
Well, you could use a code book. So you could have a set of messages and each message has a number to it, or you could have a set of words and each word has a number.
Okay, all right. So we're going to assume that you have a message that you want to transmit to the audience and you don't want me to see it.
That's right.
And so we're going to go through the system and then I'm going to come in and intercept your message and see if I can figure it out.
See this. This is our secret shared message, and we're going to go through the process of encrypting that so that Sarah will see what we've sent, but she will not see this message. In order for us to share this message, we're first going to establish a code-breaking prime. We're going to choose the number 73. I'm able to take our secret message, 43, and multiply it with 73 to get our publicly shared message 3,139. This is the number that Sarah will be able to see, but she will not know either our secret message or our code-breaking prime.
All right, Alan, what do you have for me?
Where are those transmissions you intercept?
Break this.
All right, I'm intercepting 3,139. I've got to figure out which numbers divide this number, because one of the numbers that divides this number is the secret message that I'm after. All right, ready? So here we go. This is all I can do, and this is what a computer would do. I'm going to start dividing this 4-digit number by, well, we'll see if 3 divides it. No dice. We'll see if 5 divides it. Nope. Oh, We got one!
How did you break my code?
I used my space computer and a little technique we like to call brute force division, which is what computers would use. So that was just a little tiny 4-digit number, and it took me about 4 minutes to finally find a divisor. What would have happened if that was like a 600-digit number?
If I'd given you a 600-digit number to work with, I think it would have taken longer than the life of the sun to crack it.
All right, that's a long time, and I'm glad I'm not here for that long.
Yeah.
I don't think my computer could handle it.